right, good morning. Let's get into what we're going to do today. So we're going to kind of bring this all together, talk a little bit about IMF, so hopefully you get your sheets. Unfortunately, the afternoon classes we didn't get, or the second of the 4 yesterday, we didn't get through phase diagrams, so I have something drawn on there for you. We're going to talk a little bit about some of the differences and write on this, and then we're going to start just answering some questions with some pre-responses and things like that, okay? So, we have 2 different kinds of phase diagrams. On the left, you want to label this. This is H2O, and on the right, it is already labeled inside of there, but if you want to make a better heading, that is CO2. Okay? So, there are different boundaries that you will need to understand. I'm going to show you a bit of a phase diagram today. Oh, we see right there. So, on this line, and if it's not, you can tell it's labeled as solid, liquid, and gas, solid, liquid, and gas. Notice that we have pressure on the Y and temperature on the X. Jeffrey, need one as well? Yeah. All right. January, and we always have something sitting right here.
I don't think I punched it.
I'm going to make you come all the way over and get it. All right, so on these boundaries right here, if you want to make arrows either way, it's not that complicated of a phrase, but these are the melting and the freezing. So if I'm going in this direction with a little bit of an arrow, I am going to a liquid, so I am melting. If I draw an arrow on this boundary going that direction, I am freezing. Okay? Same idea on the other line, to the blue to the yellow, I am either evaporating or I am condensing. So those are a couple phrases that you'll want to write on there. Just draw the arrows in the proper directions. I'm going to help you with a couple other ones though. So if you're confused, I'll help you out. First part's not as user-friendly as the rest. So if you have a chart like this, again, this is melting. This is freezing. This is evaporation. And this is condensation. I'd write the whole thing. I'm just abbreviating it. And you can write on either one. I would do it on the water one, personally. Yesterday, 2 of the groups, we did get through this, but we flew right at the ending of this. But when you're going, these are kind of the newer terms. When you were going below from a solid to a gas, or a gas to a solid, when you're going to a gas, that is sublimation. I'll write it right here. That is sublimation. It's sublimes. My favorite groups in high school until he died of heroin overdose. It's just a fact. The lead singer of Sublime died of heroin overdose. So it sublimes. It goes from a solid to a gas. If it goes the other direction, it is called deposition. So if we're talking about arrows this way or that way on there. Okay? There's a couple more points though. One, please label at least one of them, called the triple point. Okay, so in the middle area, and I'm not labeling this terrifically, but you have it on your sheet, so the fact that you don't have to draw it. Triple point is where you actually have all 3 phases at once. Now I used to have a video until it broke, and we can try to find one online. But you have boiling and freezing at the same time. Mind blow. It's just not boiling at a high temperature. It's a really low temperature. But what happens is if you can alter the pressure and you can alter the temperature just right, you can manipulate what phases you have. In the upper right, what I'd like you to do is make a little on this one. Make a little dotted line off of that point, above and to the side. This actual point is called the critical point, and I know I'm getting very tiny in here, so just try to hang with me here. The actual point is called the critical point. So on either graph. So just like right here. Just do a dotted line up and over. Yes, and point D. Or if you want to do point Z, either one. Inside that little dotted box, you're going to write supercritical fluid. It's supercritical. It's not just critical, it's super critical. All right, and what you want to talk about there is basically at this point and after the fact, it's really weird, But what are we talking about there? We're talking about really high temps, and we're talking about an insane amount of pressure. And what happens is with the interactions, the more pressure you have, the more, as you increase, the more that you are going to try to be packing those atoms together. There is no, let me just write it down here. There is no distinction between a liquid and a gas any longer. There is no distinction any longer. It is not really a state of matter any longer. It's not a liquid, it's not a gas. It's a supercritical fluid. And if you're like, make one please, I can't. But I can do something else. So there's one more thing I want to label on this, and I want you to really be aware. Notice that the difference is between the water and the CO2. This is rare. This is a normal phase diagram. This is actually abnormal. And what I'm talking about is this slope of this line right here, okay? And you'll have to label this somehow, and then the rest of this is pretty user-friendly. This is a, what, negative or positive slope? It's a negative slope, that's a positive slope. What it means, this is how I remember this. If you look at that, the water is basically above the solid, like it's above it, right? Here, the solid is looming over the liquid. So make a little note here, the solid is more dense than the liquid here, but here, the liquid is more dense than the solid. And I know that based on the graph, and you will need to know that. Based on the graph, that comes up a lot. How do I know if the solid or the liquid is more dense? Oh, I'm going to guess. No. Based on the graph, you can either talk about how the slope is negative or positive, or the fact that the area of the slope is above or below the other area. So I will say it one last time. This is a negative slope, meaning that the liquid is more dense than the solid. Which we know that, because in lakes, the ice forms on the top, right? It doesn't sink down and smash all the wildlife underneath. Here, CO2, the solid is more dense than the liquid. So then what does that mean for the liquids over the gas? Because of this slope, the liquid is more dense. You don't have to write this one down, but the liquid's more dense than the gas, the liquid's more dense than the gas. I hope that's the case, because gas is really spread apart. It's not very dense at all. All right, so I have a really cool demo. I hope it works. I think it will, but I got to do it a lot. I'm talking about I hope you can see it. With water, this is normal conditions, 1 atm. So in normal conditions, I hope we assume that that's 0 degrees. That's 100 degrees, okay? Here, whoa, here's normal conditions. So what's happening? I go from a solid to a gas only, right? How do I get to a liquid? How is it? What's the only thing I can do to get to a liquid? What do I have to do to it? Increase a ton of pressure. Look at this. I got to get to 5 times the pressure that we are normally, which we couldn't handle, just to be able to start to see a liquid. So I brought a little dry ice. And I have a really simple device. And what I'm going to show you today is liquid CO2. But I can only show it to you in about 2 to 3 second intervals. Because if I leave it any longer, this thing, it blows. Now, not in a cool mushroom cloud, it just blows off the top. So we're going to see what we can do. I'm going to turn on...
Shut up. Oh my God. No, stop. There he is. No, we can like the cold cuts down here. Yeah, I don't think they can. Let's just pass it until like 6 hours.
All right. So, what I'm going to do is basically, I'm going to put some dry ice in here, and then what I do is I close it off, and the gas, because it sublimes immediately, and it creates more pressure, is that the pressure will increase, and eventually I'm going to move it back and forth, and I'm going to do it under here. There it is. And hopefully you can see some, I'm going to turn off the lights. Maybe you can see some liquid moving around, and it's not overly crazy, but it's something that you normally don't see. And then we're going to play with dry ice with one other way. So. Of course, it doesn't fit.
Oh, perfect. Just smash them out. Well, just grind it in there. Hit it on the table. Smash it. Now close it off. You can melt it a little bit. Yeah, what if you start breathing
I
out?
love how everyone's an expert.
You're welcome.
My extensive knowledge of CO2, this is my 4-step plan. Yeah. Give me your pencil.
That's what you're gonna do. It's frozen.
And pencil's done.
Nothing contaminated.
Okay, did not think this would be the issue. It's like stuck in there. It's exciting.
What color is it?
It's just colored, it's cleared. Like this is why at the ending of it I'll be like, oh, that was a lot of work for what? And this is what we're gonna do. I'm gonna put a couple pieces of ice. Hunter, the dry ice killer, I suggested to let it melt a little bit. So we will get to that in a second. All right, the other thing I do want to show you is about surface tension. So I have a cool thing to do with that. So I just got to get some hot water. I'll be right back.
I wouldn't try it. I'm like, that's expecting you to really
It is a heavy
yours too. They were going up and down on my table. You can see what on there. I figured out it's just a few times. No, going up just yeah, the pressures were they were going up so high that too high. So they had to
Here we go.
with glass of direction. And then we're
So what I have,
Just grabs.
I wasn't gonna do that. So that's subliming. It's going from a solid to a gas right away. You can do cool stuff like so what I have is some soapy water. And it's a headband. I kind of watered down the soap. I'm a little worried about it.
Oh no, she fell.
Do it one more time. Happy January 13th. Surface tension. All right. I'm like, let's try this quickly now. Oh, there's a piece in there. I'm gonna try it. I don't know if it's even gonna work. So there's really small pieces. So I'm gonna try to film it. might be off. All right, we'll just put a bunch out, and then we'll pack it up, and I'll show it to you at the ending of this. It's all right. Mr. Sperduto tells me they used to play with dry ice. I worked at a packing company, and they would they'd put it in their mouth and then flick it on their tongue. They would dance on their tongue, but they couldn't let it stay on there because it would obviously burn their tongue. So, all right, so we'll get back to that. It's pretty cool, but we'll get into the rest of the stuff for today. Let's let that go. All right. All right. So a couple pieces of information. First off, if it's not running tonight, I'm going to send a video. I'm potentially heading out after this hour. One of my kids is sick, so I came in to make sure I got this lecture done, but I might be heading out. I'm not sure yet, so it's in the air. So if you can check in, or just even look in here during the day if I'm not in there. Maybe I'll send an email to everybody, but the chances are I'm not here tonight. So I'm kind of trying to do a major review right now as well, but I will send a 30-minute video out to everybody as a supplemental review. So apologize, but we got to do what we can with what we have. All right?
Are we going to review tomorrow night?
We could. Yes. We could. Well, I have a staff meeting though right after school, so it'd have to be later. This Thursday we have a staff meeting, so I guess to be continued.
You could do it at Hulk ground. You got a big hospital.
All right, so on your sheets, here we go. We're going to talk about situations in all sorts of different kinds of ways. One thing on your worksheet, number 13, I believe, or the one above the heating curve, we are not having to do. We're going to get rid of a thing called the Clausius-Clapeyron equation. We are not going to need to do a plug and chug at all. This is about just concepts, and if you feel like, man, I don't have enough to talk about, believe me, we do. I have 4 sides of a piece of paper to go through today yet. All right, so on your sheet, here we are. What if, this is a nice little review right away. What if I had a greater vapor pressure, greater boiling point, greater volatility, greater surface tension, greater viscosity, or a lower freezing point? I just picked some different ones, and maybe I should have changed that up a little bit. What's up with my IMF strength? So this will kind of help us in the long term. So the one that is the most confusing for most are vapor, when it is concerning vapor pressure. That's the pressure that is actually at the surface of a liquid, and the greater the vapor pressure, that means the more that the molecules are escaping, so it will boil easier. So if it's easier to escape, it's not attracted to itself, so the IMF strength would be less, okay? So the IMF strength would be less. So I just basically have IMF strength, and then the greater the vapor pressure, the lower the IMF strength. The greater the boiling point, what it means is you need a higher temperature to make it boil, so you have to overcome attractive forces, and it's going to take more energy to do it. So that means there would be greater IMFs. It'd be stickier. It'd be stickier, so it'd be harder to remove. Volatility. You don't remember that term? We've talked about it way in the past. Volatility is actually related to vapor pressure. It's how volatile means how easily something can evaporate. So if you smell something like, oh, that alcohol, that's really volatile, it means the smell's coming off really easily. It's evaporating really fast. So if it's really high volatile liquid, that means also then you have a lower IMF strength. Surface tension, we've talked about that quite a bit. Oh, and I didn't get a chance. I will announce who won the penny war. I didn't get to look at him last night. I was working on this. So the greater the surface tension, the greater the IMF. Viscosity is how the flow, so the thicker it is, the usually the more attractive they are. And then lower freezing point. What that means, this is what people get confused with, but I try to keep it really straight. Besides volatility and vapor pressure, which are kind of synonymous with each other, everything else, if it's greater, IMF's greater. If it's less, IMF's less. So a lot of times people get confused with boiling point and freezing point. If you have a lower freezing point, that means it takes a lower temperature to make it a solid. That means you have to slow it down until those attractive forces are greater than the kinetic energy. So that means there's literally like no IMFs the lower the freezing point. So that means the lower the freezing point, the lower the IMF. And a lot of people get confused by the freezing point part. Well, wait a minute, if it's a high IMF, shouldn't it be a low freezing point and a high boiling point? They're both the same. If it's a really high IMF, they're sticky already. So if you slow it down just a little bit, oh, I'm stuck together. I'm starting to attract to the other atoms in there. So this is a nice little, right away, summary, and I'll tell you now, not that I'm dismissing reviews, but I'm putting a lot of stuff in that I was going to be doing tonight as well, because I tried to put in some stuff this morning once I found out that I might not be here, but anyway, we'll see where we're at on all that. So here we go. A bunch of different things. I have more writing than you'll want to do, but what you're going to be doing is probably writing 1 to 2 sentences on potentially explaining things. FYI, on your worksheet, even if it doesn't say explain, then that's my fault. You need to have at least 1 sentence of explaining everything. If you just circle something, you'll lose points. You need to explain something. Something. You do not, and this is important, my first year ever teaching AP, I made them write what an H bond was or what a dipole-dipole meant every time. You don't have to explain what they are. You have to explain which one's stronger or weaker and then how that relates to surface tension, freezing point, viscosity, whatever. So if you're wasting time writing every time, well, H bonding occurs between H's and FO or N, and because of that, it creates a stronger dipole, and because of that, it's like, no, it has H bonding, which is stronger than blank. And because of that, the whatever is higher or lower. Okay? You'll see that today. So here we go. A bunch of different scenarios. Some of these might be really similar to test questions. It's really important. You got to understand this is kind of a stepping stone. This is a segue to a lot of other chapters and explaining a lot of different things. So today, we're going to kind of come in and out. You're going to work with some people by you. You're going to kind of work on your own. Sometimes we'll do it together. Okay, so this first one, we'll do this together. Which one has the higher boiling point? So with all of these, what do I have to do first? I have to diagnose what IMFs I have, right? So what are the IMFs in all of these? Just anyone want to shout this first one out? We're going to do this one together. So what's that IMF? That's H bonding, dipole-dipole, dipole-dipole. Not all H bonding. And I did this one as a trick. Everyone's like, oh, H's. It's not all H bonding, right? So I would suggest writing that kind of small underneath those. You can even just write DD for now or something like that. You have to know. You can't just jump into the explanation. You have to know what each one is. And I'll show you later. You might have to draw it out. Here, you don't really have to draw it out. So in this one, which one would have the highest boiling point? Well, it'd be the one with the H bonding, correct? Because you have to overcome that. Now, this is a lot longer than you have to write. So what I would do is just read it and then try to write this in 1 sentence. That's kind of the exercise that I'm hoping that we do today. So I wrote this. This is my own words. I didn't look any of this up. I kind of tried to do it myself as well. HF has the strongest IMFs, the higher boiling point. The greater the amount of energy that is needed to overcome the IMFs, HF will end up boiling at the highest temperature. Try to do that in 1 sentence as much as you can. So HF has the H bonding is stronger than dipole-dipole, which would cause it to have the highest boiling point. Or you could say that it takes more energy to overcome the IMFs. It's always, if you're ever like, I feel like I'm repeating the same phrases. Let me just say that one again. It takes more energy to overcome those IMFs. And if you're like, I still don't feel like I'm specific, you could just say it to go from a liquid to a gas. Done. Okay? And I'm trying to give you different scenarios because I know how this works. You start to feel like, man, I feel like I'm always saying the exact same. This thing is the lowest IMF, and that's why it's this one. You feel like you should have a little bit extra related specifically to that scenario. So in this case, I'm talking about boiling point. So I'm talking about separating the molecules from a liquid to a gas. So I want to separate them completely. Okay? So, feel good? No? Yes? We'll see. All right. Again, scenario. We have a ton of them. Some of them will have a lot of writing, some of them won't. Next one, lower freezing point. So, what are we dealing with here? Actually, you know what? I'll give you 2 minutes. Figure out this one, please. I'm going to go back to you. Work with each other or by yourself. If you're just going to wait for me, that doesn't help.
Draw all these except it was because actually they are the larger the so neon because it's higher boiling point. So that's lower.
I'll try because it's
All right, I got a hammer. We're gonna smash some CO2 after this. Yes. Erica, what do you got? What are these? What are they all?
They're all London.
Yes, they're all London forces, right? So when they're all London, then what does it come down to in general? Size of the atom, right? It's really weird because when we've been talking about forces before and strength, it's always the smallest because it's closer to the nucleus and it's holding on electrons. Here though, the reason a London force exists is that the electron cloud is affecting other electron clouds. So the larger the cloud, the stronger the IMF. So in this case, the answer is which one? I want the lowest freezing point, so it would be the smallest one. Now I wrote a lot more than you need. But basically, you want the lower freezing point would result in a weaker IMF. And the smallest electron cloud would have the weakest London force. Done. Which is, and then you gotta say it, which is neon. And I don't even know if I said the answer.
Yeah.
Oh, there it is. Neon would have the weakest IMF. Maybe just this last sentence is what you really need. I wrote, it's good to hear it all. Again, these are just my own words. Lowest freezing point would involve a substance with very weak IMFs. With very little attractive force, the substance has to have very little kinetic energy to be able to attract itself. With all substances being London forces, neon would have the weakest IMFs, having the smallest electron cloud. Neon would have the lowest freezing point. Again, I'm being wordy.
Could you say anything about, because they're like, it has a smaller electron cloud, so it's tighter packed, and then when you're slowing it down to freeze, it would be easier to bring them closer together? Is that not making any sense?
Don't go to, I know what you're saying, but stay away from that path. Right now we're just talking about IMFs and attractive forces, okay? So I know what you're saying with the nucleus. We're going to stay away everything from the nucleus right now. We're just talking about the electron cloud itself.
Why does more IMF mean smaller electron cloud?
Because what we were talking about with those electron clouds get uneven, and then it causes the electrons to be on one side of the cloud or the other. I wish I had an image on this right now. And then it causes the next cloud to move the electrons over, and it makes this really weak dipole. So it has nothing to do with the nucleus itself. It's the electrons either being there or not being there, and then it makes this little positive and negative side.
So it's, okay, so we're dipole that results.
Yeah, so that's the only attractive force. We're not talking about the nucleus thing.
Right.
Because once you bring in the nucleus, that's a strong attractive force. That's something different.
Okay.
That's another hand of thought. All right, let's get to the next one here. All right, so draw two different structures of C2H6O. Compare boiling points. So what I want to do, anybody have an idea what I could draw? What can I draw? We're going to draw them underneath together. What's one? Maybe you know the name, maybe you just know how to describe it to me. Zigzag is a type of drawing. An alcohol, yes. Good way to use our terms. An alcohol, what's another one? There's another name using an oxygen. A what?
Ester?
Close. An ether. Those would be my two options. It says compare the boiling points. So if it just says that, what you need to do is you need to talk about both. You need to, in AP Chemistry, make sure that if it's asking about two things, you need to talk about both. So this is what you should do. First sentence, you declare what IMF is in each, the strongest IMF. Second sentence, you say which one has like the higher or the lower. Okay? You don't just say this one has dipole, that is lower. Like, whoa, you're not comparing anything. So let's talk about this. What is the strongest IMF in this one? H bonding right here. So this is H bonding. What is the S or the ether?
In London forces.
If it were dipole, it has to be polar. If it's London, it has to be non-polar. This is extremely symmetrical, yes? Like extremely symmetrical. So the minute it's all symmetrical, everything's canceled out. So this is London. This is LD. You understand? Like, well, yeah, but there's an O there and everything. Yes, I agree. If this stopped here, that would be a dipole. But it doesn't. It cancels itself out. So just make a note. You might even want to write on the top, like non-polar. Like it's kind of key to that word.
So, if you took away one of the H's on the London port, or would that be dipolar?
Yes, I mean, I guess it depends what goes there. Something would have to be there, though.
Just like a lone pair.
Yeah, I mean, I'll play along and say yes. Just with like the carbon and stuff, you wouldn't have that.
Okay.
You know, carbons have to bond 4 times. So, I mean, but I get what you're saying. Yes, if it's uneven, then yes, it'd be dipole. So then what's the answer? What would I say then? So first sentence I would say the alcohol, and you could say it that way. The alcohol would be H bonding, while the ether is London dispersion forces. So which one's higher, boiling point? The alcohol or the ether? The alcohol would have a higher boiling point, and then I would say because H bonding is a stronger IMF. Or the ether is a lower boiling point because it has a weaker IMF. You have to actually declare which one is a stronger or weaker IMF. Note, I did not go into detail of what is a London and what is an H bond. And I don't have anything waiting to come up, so I'm just verbally saying it right now. Yeah, Layla.
So for the test tomorrow, we love to use...
Friday.
Sorry. Are we allowed to use abbreviations and stuff? Like when we write on the...
Yes. Yes. No, you have to write London dispersion force. Everybody else can just make a squiggle. Sounds like Rory's goats. When they have frozen water out there. I'm just playing.
Take me on holiday tonight.
See where the debris goes on.
It's just a disaster. All right, let's move on. All right, next one. What if we're talking about vapor pressures and I give you a situation already? So it is not your job to know that you have to acquire these numbers. You don't even really understand where these numbers came from. I'm just saying the vapor pressure in pascals, whatever, the larger, the smaller means that it's like a higher or lower vapor pressure, right? So right now what I'm saying is, what if you found out that A has an 88 PA, 680, and 155? So this means that that's the lowest vapor pressure. This means it has the highest vapor pressure. Translation, okay? How could I take that information? All I'm wanting to do now is under boiling point. I think I wrote it like, where is that? Underneath, we're going to just, I didn't do a title with BP. I want to now talk about its boiling points. So we're going to say blank, like A or B or C is greater than A, B, or C, greater than A, B, or C. So the strongest to the weakest boiling point. Okay? So let's talk about this first, because I think it's important to label this, and I don't have everything labeled. Which one, it's all about IMFs. Which one has the strongest and which one has the weakest IMF? So talk about it, someone. A, B, or C, which one has the strongest and weakest IMFs? Yeah.
When, like, you know how
Yes, this is vapor, so this is a one. I was thinking
If you freeze it, it actually stays exactly it's more if you get to gas and then start to separate. But we'll talk about that because what you're talking about is two different things, which I'm going to show you how to do by breaking it apart like F, like say F, F2, F, that's different than F2, F2. F to F is different than F to F2. We're talking about inter versus intra. Okay? There's a big difference.
Intra is like
H in that, right? Like, so H is here, that's here, interest here. H is here, then it's
That's what I see.
All right, which one has the strongest IMF, A, B, or C? A, because it has the lowest. If you didn't write this down, just put a up or down arrow, and I don't have that to come up on here. That is the strongest IMF. So then, which one? B is the weakest? So then what does that mean? Which one am I going to come up first on the biggest boiling point? A, then C, then B. Because that is the strongest IMF, that is the weakest. So that is the leap that you need to be able to take. You need to understand that vapor pressures are opposites to the normal IMF's increase-decrease situation.
Why?
Because if it has a lower vapor pressure, that means it's sticking to itself more. It's more attracted to itself. It's not evaporating as fast. So that means it would take more energy to cause it to boil. Okay? This one is more, and this might be a note you want to write. This is more attracted to itself. This has hardly any, this is low IMF, so it's not attracted to itself. It has, like, it's not, stickiness is a nice way of thinking about IMFs a lot. This is much stickier to each other than that. So then if you start to boil it, it just leaves. So vapor pressure is the same way. There's nothing holding it together, so it just can jump out of the solution. Okay, vapor pressure is the one, though, that everyone gets, if they're going to lose on something, that's the one that gets them. All right? All right, let's talk about this. Higher boiling point. So what am I dealing with this? This one we'll do together, just to make sure we get enough time with everything. What am I dealing with all those? LDs. I'm dealing with LDs on all of them again. All London dispersion. So, what's the deal again? I want to do this because we had one that just was NE and KR or whatever. What about this one? What's the situation here? Still the larger electron cloud, still the larger structure. Okay, the larger the structure, there's two ways you can think about it. If it's larger mass, it takes more energy just to have it escape. Just think of it that way. If you have a small little prisoner and a large prisoner, the little prisoner might be able to escape a little easier than the large prisoner. But it's also about being attracted to each other. The larger the cloud, the stronger the LD. So, just looking at this, you don't even need to have it all down for structure. Which one has the higher boiling point, which means I'm looking for the strongest IMF, which means I'm looking for the largest molecule. So the answer is CH. Yes, Kevin?
If you're looking for the largest molecule, then why was it krypton bigger than neon?
The last one was the lower. The title on that one was lower. It's in the upper left of your sheet. Or, no, yeah, middle left.
It's freezing.
Oh.
Right. But freezing point and melting point are the same ideas. Higher means stronger, lower means weaker. That's right. So due to all the structures having the same type of IMFs, the large molecule will have the highest boiling point. CH18 is the largest and has the strongest LDs. Now, I didn't comment on electron clouds, but that definitely is a very appropriate and correct conversation. This just did not go the way I was hoping. Never had an issue with this before. All right, next one. All right, is this on the back now? All right, we have a bunch of things with interactions. Just have a couple more things we got to do here. And I got to make sure we have enough time, so we got to get going. All right, I'm going to just go through this quickly here. If A has higher viscosity than B, ... All right, which one has higher vapor pressure? So let's just quickly, we're going to write underneath here. I don't have this here. Which one has the higher IMF? If A has a higher viscosity than B, which one is higher? Right?
Wait, quick question. Viscosity is the ability to flow through?
Yeah, and you can also think of it as the thickness of the liquid. So A is the greater IMF. So underneath A, I'd write greater IMF, or an up arrow, and then B, I'd have a lower arrow. So, which one has a higher vapor pressure? What? B, because it has weaker IMFs. The higher the vapor pressure, the weaker IMF. What about lower freezing point? B, weaker IMFs. And then higher boiling point would be A, stronger IMF. Which one's more volatile?
What does that mean?
B, because volatility is the ability to evaporate easily, which is basically saying boiling point, even though you're not evaporating isn't necessarily boiling point, but it's, you can think of it similarly. Obviously, there's a difference in temperature. Okay. What else do we have? Oh, all right. We're gonna quick. Geez, a lot of stuff to do. We'll do a cooling curve. We gotta fly a little bit. If we don't finish all this, I can easily make a video to finish this. But I spent too much time with the dry ice. All right, I want to do a cooling curve. So a cooling curve looks like this. All right. Now I have 1, 2, 3, 4, and 5. So it says 50 grams of water at 450 degrees Celsius to negative 80 degrees Celsius. Amount of energy that released from H2O. So if you have access to your worksheet, we need values from number 14. I didn't supply all that because I know you have access to it right now, okay? So what do I need to do? I need to go through this first. And if this helps, this is my gas. This is my gas to my liquid. This is my liquid. This is my liquid to my solid. And this is my solid, which we've been talking about. Okay, this is what you need to be doing on your lab as well, which is due tomorrow, I believe. All right, so what do I have to do first? 1, 3, and 5 are MCATs. So I have 50 grams of water. I look at my sheet. I'm a gas right now, so steam is 2.0 joules per gram Celsius. In my opinion, this is the hardest part, the temperature, only because you start to get confused. What am I ending at? Where am I ending right here? That's 100. That I'm getting to the melting, or the boiling point. Or if you want to think I'm starting to condense. So I'm ending at 100. Where am I starting? According to this situation, 450. Woo! And there I am. It's the first one. If you have questions, just shout them out.
Wait.
Just say it.
Yeah. You would put 100 first? Wouldn't be...
It's initial minus final. Sorry, final minus initial. So I'm ending at 100. I'm starting at 450.
Oh, yeah.
All right, now I'm doing a phase change. So now I need to utilize enthalpy. All right, so I have 50 grams of water. I need to get it into moles. So is this enthalpy of vaporization or enthalpy of fusion? Vaporization. So this should be the larger value because it takes more energy to separate or condense. So it's 40.7 according to your sheet. And then what I'm going to do is just put it into joules.
What is that? 4.40?
It's on your sheet too. You can get your homework sheet out.
Would it need to be a negative 40.7?
We will talk about that. Yes, you've preempted me. Yes. Very good. So, we were gonna calculate a couple, and I was gonna show it, but actually with time, I'm glad you brought that up now. This value right here, if you calculate this, you get a negative number, you're gonna have a negative value. Does that make sense? You're cooling it, you are releasing energy, right? You're releasing energy. So the energy's not going in. So, it's very important that you have all the same signs. To remedy that, you can either fix it there or you could manually do it at the end. But just please recognize that if you get your first answer, this is where I was going to go with this, is that usually your first answer will reveal to you, if you forgot or you're not thinking about that, usually when you start heating and cooling curves, you're not thinking about, oh, do I get a negative or a positive number? It will show you, like, oh, I'm going to have a negative or positive. Sometimes the negative or the positive doesn't matter as long as they're the same. So if you have all, I mean, you can't have a negative and a positive. Sometimes the question is just how much energy. Well, you're not going to even have a negative number anyway, it's just an amount. But that's that one. I'm going to go through all this. What I'm probably going to do, because I may or may not be here, I'm going to, for surely, whatever we don't get to, I will make a quick video and send it out in an email and put it on the website as well of all the other parts in case we don't get through it all. So that will still be there for you. But let's just keep going. So number 3. Now I'm here. I want to make sure we get all this. I still have 50 grams of my substance. It's just now a liquid, not ice. All right? I have now a different one, and I'd like to use the one that we've been working with is 4.184. I know that's not on your sheet. If you rounded it to 4.2, that is fine. What's my temperatures? What minus what? 0 minus 100, good. Right, I'm starting at 100. Sorry, right here. I'm ending at 0. And I'll get a value there. What is the table doing?
I got one really too. What's the toilet at?
For if you already converted the moles, you wouldn't need to do it again. But I don't have that value. Is it 6.02? 6.02. I'll make that negative right away.
Well, I'm done already though, so.
Light. And then number 5, to finish this up. 2.1 specific heat for solid ice. 2.1. And then what's my temp on the last one? I know some of you worked ahead, which is great. Negative 80 minus 0. Please note how I'm doing that. You can put a temperature on each, but you got to at least put a temperature on the second one so it's all consistent. And then you'll have a value. Kevin?
Can you just throw a negative at the end for 2 and 4?
You could.
Just because you know you're...
Like you'll recognize, like I didn't do it there, or else when you start calculating, you'll be like, whoa. You got to have the same sign. You can't have positives and negatives within different ones. And what do? I add them all up, right? I add them all up.
How are they not going in?
I don't know. It's just so much smaller than I thought it was going to be. And it's, oh, that's cold. Really cold. I needed a mortar and pestle. So, what I'm going to do, I'm realistic on the time here now, is we only have a couple minutes left. Yeah.
Okay, so for our most of our calculations, we're using our own values that we made from the lab, right?
Yes.
Okay, what will we use?
This is good for you.
Our change of temperature, like we're using 0 and 100.
Well, you might use 99.1 or whatever you
so
have.
We're just gonna use that instead.
Use whatever you can have. If you don't quite know, then you might have to default to a more standard value. Like, you have to be a little flexible with it.
What do
Okay?
we use for grams for those calculations?
It depends. If you use one that I pre-made, it was 250. Otherwise, you were supposed to know how much liquid was in there. So whatever the volume was, that's the number of grams. You might have to estimate. Jeffrey? Good question. A couple people came in. So guys, when you're talking about solid, liquid, and gases, back in middle school, when you talk about solid, liquid, and gas, you said things had like a definite or a fixed shape or a definite or fixed volume, right? Or no set shape or no set volume. So for example, let's talk about a liquid. A liquid, which one is it? A set volume or a set shape? A liquid. Set volume, but the shape is not set, right? It's there's not a definite shape because you can put a liquid in any container and it takes the shape of its container, right? But solids and gases are different than liquids. That's all that's referring to, okay? What I'm going to be doing, even if I am here for a while, I don't know, I gotta call home, I will be making a video showing the screen of the rest of this. It is really important that you watch it, okay? So what do we have, a page left still? I'm gonna be drawing it all and filling it all out, so it's really important that you do that. Watch it, okay? If you're like, oh my gosh, there's something more work. We gotta make it work out somehow. Work on your worksheet, cross out number 13, please.
And this all here, right? Let's go through the liquid solids. Okay. We're doing. The question is,
Hey Matt, can you go back in the script? Give us a red button back.
so
It's like, yeah, it's just relax here.